Hi guys, welcome to another episode of the Iraqi Nutrition Podcast. I'm your host, Juma Iraqi, and today I have brought back Dr. Jose Antonio. Joey, how are you doing today?
I'm doing really good, and and I'm very happy to be back on your show. So
Thank
we're
you
gonna
so
have some
much.
good times there.
Yeah, absolutely, and thank you so much for agreeing to do this podcast. Today's topic is a bit about research, just what goes into the research process and what actually researchers do. So I think it will be a really interesting podcast. So we've done an episode before on high protein diets, but for people that haven't watched that podcast, could you just briefly give us an introduction about yourself?
Yeah. Currently, I am a associate professor at Nova Southeastern University. That's in South Florida. I teach in the exercise science department. I teach exercise physiology, a research course, as well as sports nutrition. I got my PhD way back in 1993 at the University of Texas Southwestern Medical Center. That's in Dallas, Texas. And also I did something that was rather unusual. You don't find too many people doing this. In fact, one of your past guests, Brad Dieter, is actually doing a postdoctoral research fellowship. I actually did one as well in the field of metabolism and endocrinology. And after my postdoc, I've basically, in the last couple decades, focused most of my research in the field of sports nutrition and dietary supplements. In addition to that, I've also, done some work with athletes. Initially, oddly enough, way back when with bodybuilders, this is back in the 90s, but I've really shifted my focus more into the endurance sports, mainly because I myself like to do a particular endurance sports, which you've seen. I posted on Facebook. I do quite a bit of stand-up paddling, paddleboarding. I even compete in some of the local road races, some of the local races that are obviously it's in the ocean. And I actually work with some elite stand-up paddleboard racers. And in fact, I'll talk a little bit about one of my friends who I helped. I helped her train for you would almost call it the Super Bowl of paddling. It was a race, a 32-mile race. I don't know what that is in kilometers, but it's really far. From Molokai Island to Oahu in Hawaii, and it was basically across the ocean. So I do, a lot of my science friends, we do similar things in terms of we not only do research in the lab, but we actually work with athletes. And I think, at least in the United States, it's actually quite common. I don't know what it's like elsewhere, but we actually seek to work with athletes. And I think all of us who work in the sports science field, we also are athletes ourselves, and I think our interest in the science part stems from our original, love of athletics. So we try to do a little bit of everything, some of the applied stuff and also some of the lab stuff.
Yeah, excellent. And I think it's a great thing that you mentioned this, because you often hear of people when a new study is presented on exercise or nutrition, and people say, well, these scientists don't know anything of how the real world works. They're just lab rats, and they don't work with athletes. They don't have any athletic backgrounds. And I saw this posted on Facebook last week, actually, from someone, and I started to think for myself is that I don't actually know any research scientists in sports that haven't had an athletic background or haven't worked with athletes. Because you see, like, especially in the UK, you see a lot of the researcher, they work closely with a lot of the soccer teams. Like Liverpool is a good example of that, where Dr. Graham Close and Dr. James Morton has been working really close for them for a couple of years. I don't know if Dr. Close worked so much with Liverpool. I know that James Morton did a lot, but they worked close together, and I know that Dr. Claus was probably doing more with the rugby team, right?
Right, yeah, I believe so. And I mean, like, for instance, some of my closest friends, one of my fellow colleagues at Nova Southeastern University, Corey Peacock, he played football, American football in college, and he currently works with the Black Zillions MMA team here in South Florida. And for people who follow MMA, they know the Black Zillions gym.
Yeah.
One of my good friends, Jeff Stout, he's at the University of Central Florida. He's a black belt in judo. He competed in judo. Actually, his kids also compete in judo. And I don't know if you've interviewed Darren Willoughby yet. He's probably the largest scientist in the world.
Yeah, I actually had when we recorded, I know that you said in advance before I interviewed him that he was probably the largest scientist that I would ever do a podcast with, and I was like, he barely fit in the screen when we did. He was I was really impressed with the size of him, and I've also seen a couple of pictures of him as well.
Yeah. Well, you got to tell him to stand like 20 feet back.
Yeah, exactly, to get him in the frame.
Yeah, but you know, like you said, I think a lot of us, that's why we're in this business, why we study sports nutrition and sports science. We love athletics. I mean, I almost would find it hard that you would study it, but you don't do it. Like, you don't find a sport or exercise you like to do. To me, that's kind of odd. It's like, well, that's why all of us study this stuff, because we want to understand either why we can or cannot do a certain skill or athletic event.
Yeah, exactly. And one thing that I think a lot of people might actually not know is a lot of researchers, they do a lot of studies to that would benefit their athletes, and the studies actually never get published because they don't want to give all the secrets away.
Right. And also, they do studies to benefit themselves.
Yeah, exactly.
They want to see what they can do to help themselves. So, yes, it goes both ways, yes.
Yeah, exactly. Okay, let's start off with the question. And the first question is how would you define a scientist?
You know, that's an excellent question. In fact, it actually comes up in I teach a research methods class at the university. And more often than not, someone will say, well, okay, people call themselves scientists, but what exactly is a scientist? You have all these people on social media claiming to be evidence-based or scientific. Does that make them a scientist? And in a sense, you know, the term scientist, there's no legal definition for it. If your grandmother wants to call herself a scientist, you know, be my guest. Anyone can call themselves a scientist. So what I'm going to do is really define it the way professional scientists in the field of sports science or sports nutrition science, how they work. And it typically is this. I mean, most scientists either have a PhD, and in some rare instance, you might have a medical degree, but there's not many MDs who do research in sports science. So typically they've gone through your traditional schooling, get a PhD, work at a university for the most part, or they work at a private clinic. But let's start with universities, because that seems to be the most common way of being a scientist. Typically, you have to have a research agenda, and you're familiar with a lot of the scientists throughout the world. You know, some might focus just on one supplement. Let's say it's protein. Some might focus on heavy resistance training, looking at periodization schemes. You know, different types of weight training regimens. Others might have a much broader scope and look at like nutrition in general. So having a research agenda, I think, is just one aspect of being a scientist. So let's say, like, for instance, in our lab at Nova Southeastern, I've been focusing a little bit on protein, but I'm starting to also expand it to looking at things like the gut microbiome as it relates to probiotics, and even studying training for stand-up paddle boarding. So there's what I call my research agenda. Now you have a research agenda, and typically within the university, to get a study started, you have to go through a process. What's interesting is a lot of people aren't familiar with this, particularly if they've never worked at a university. You have to get approval through the university, submit something called an IRB, which is an institutional review board, and a proposal. And basically, the university has to be allowed to do this with a minimal amount of risk, or to minimize the risk to human subjects. So you got to get it approved through the university. If you happen to do animal research, believe it or not, oftentimes the standards are more strict. In fact, a lot of my original work when I was doing my PhD and postdoc was all on animals. And they were very strict as to what you could or could not do with animals. So again, a lot of this stuff has to get approved before you even start to do the study. So let's say you submit it. This can take anywhere from a month to, 4, 5, 6 months. And that's the part people don't see. They don't realize just before you even start it, you've already spent at times half a year trying to get this thing sort of honed down and approved. So you get it approved, and then you actually go through the process of research. And I think this is where I think a lot of people in social media, they don't understand sort of the trials and tribulations of doing actual research. And I think experience is a brutal teacher. It's explaining the research research process to someone who doesn't do it or has not done it is sort of like explaining how you swim without ever going into the water. It's one of those things where you can sort of write down the bullet list, this is what we do, but if you don't actually do it, it's just kind of a weird thing. And believe it or not, one of the hardest things to do, at least in terms of dealing with human subjects, is recruiting them and keeping them. And you think, well, that's got to be easy, you know, people all want to volunteer for studies. Well, they all want to start a study, but a lot of them would just want to quit because they don't want to stick with it. I mean, and you just build that into your proposal, you know, getting subject dropouts and things like that. So let's say you get the study approved, you do the study. Typically the process after that is you present the study at a conference, whether it's a conference in Europe, a conference in North America. It doesn't really matter as long as you present it. And then if the data is interesting enough, you publish the study. And again, it goes through that peer review process depending on which journal it goes into. It can take anywhere from a few days to sometimes all over a year. So the peer review process, it's certainly not perfect, but it's the best thing we have for now. So going through those steps is what the traditional, and I'll call it the professional scientist does. Now, someone asked me in class, they said, well, if you're published, does that make you a scientist? And actually the simple answer to that is it actually doesn't. And in fact, oftentimes scientists put their lab techs on papers just because it's, you know, sort of a nice gesture. But it doesn't mean they're scientists. Oftentimes the scientist is the one who comes up with the research idea, submits the IRB, and is the one who basically runs the lab. And if you don't have those other components, the mere publication of a paper does not constitute being a scientist. Certainly not in any professional sense, because in a way anyone could submit a paper, particularly if you're writing a review or a meta-analysis. So in terms of being a professional scientist, I think you have to have a research agenda. You got to submit things to the IRB, get informed consent, particularly if you're working with humans, present original data at a conference and publish. I mean, those are the general steps.
Excellent. And a bit back to the one thing that you said about getting subjects to the study and actually keeping it. I know that the Norwegian School of Sports Science sometimes complain that it's really hard to actually get subjects and keep them when they're supposed to do muscle biopsies on them, because a lot of people have heard that it's really painful and don't want to experience it at all. And you can't like really force people to stay in the study as well. So So that's another issue that a lot of people, because like you said, I think a lot of people don't understand how much work goes into actually doing the research and the whole process of getting it approved and then getting it published as well. And it's really easy to just sit on social media and just pick the papers apart and criticize all the things that weren't done and that should have been done, without realizing that even though research is a good thing, it also has some limitations to it.
Yeah, and in fact, like if a paper gets published today, oftentimes the idea for that study was more than a year ago. And I don't think people realize that, in a way, scientific research doesn't proceed super quickly.
Yeah. We
come up with all these ideas, and you know, I tell people who want to get studies done on a particular supplement or whatever, think in terms, if you want something published next year, you got to start something right now.
Yeah.
And for a lot of people who aren't familiar with the process, they're like, wow, that's a real long timeline. I'm like, actually, that's a normal timeline. And it's always easy to be, you know, I always say it's sort of the keyboard warrior or the person who is the constant critic, that there's always something you could do that would further enhance a study. But you got to think of research as sort of a crawl before you walk before you run process, where you don't do the most complicated thing first, you do the simplest things first. In fact, and then after you do that, you sort of build upon that. Like for instance, the high protein diet stuff. The first study I did on that was, how about we just get a bunch of guys and girls just to eat a lot of protein and see what happens? Simple stuff, see what happens. Then the study that built from that would be, okay, let's get a bunch of guys and girls to eat a lot of protein, but now we're going to change their training program.
Yeah.
So everything is sort of this stepwise process of building up, whereas one study comes out and people are like, well, why didn't you train them this way? Why did did you get moderately trained people? Why didn't you get really highly trained people? And it's like, well, yeah, you can do all those things. I mean, but I would say give it a shot, try it, and see how successful you are. But no one ever does the most, well, let's put it this way, no good scientist ever picks the most complicated thing first. They do it sort of in a stepwise fashion. It's almost like telling a story. You got to start with the introduction before you get to the body, before you get to the conclusion. There's a series of things you got to go through. You don't just do everything at once. It would make no sense that way, and it would be a waste of time, actually.
Yeah, exactly. And I think sometimes when these acute studies gets published, a lot of people are really quickly to just say, this doesn't matter, it's just acute, it's just an acute study. But usually the acute studies are often follow up by long-term studies. They actually just publish the acute study first, and then later on down the line you'll see that long-term study are published.
Yeah, and also it also points to some studies tend to be mechanistic. For instance, these acute muscle protein synthesis studies tend to be quite mechanistic, whereas when you look at some of the longer term studies where you're just looking at an outcome, they tend to be much more applied. So there's a time and place for both kinds of studies, and both have limitations. And I forget who it was, but someone said that anytime you highly control a study, you lose some of the applicability. Anytime you have a very practical study, you lose some of the control, and there's this constant trade-off. I mean, it's like, for instance, one of the better, when you're looking at acute muscle protein synthesis, a really great model would be the single leg training model, where one leg trains, the other doesn't. You basically have a contralateral control. What better control than the same person? Of course, the trade-off is no one trains like that. They're like, well, who trains just one leg? But again, you're sacrificing control for applicability. In fact, the same thing could be said for animal research. I did, a lot of people aren't aware of this, but I've had research experience with goldfish, rats, cats, dogs, quail, and guinea pigs. So I think that's 7 animals. In fact, I was at, way back in the 80s, I did a summer internship at Leiden University in Holland studying goldfish muscle. So I've done a lot of animal work, and what's the beauty of animal work? It is tightly controlled. When I did my studies on rats and quail, they lived in a 12-hour light, 12-hour dark cycle. Humans don't do that. They got fed the exact same food. Humans don't do that. They got given the exact same protocol, whether they were in the control group or the training group. You don't ever see that in humans, ever. Tightly controlled, tightly controlled. But what's the trade-off? The trade-off is it's still an animal. Yeah. And I always tell people, do you feed your cat and dog the same things? No. Does your dog eat the same thing you eat? No. So clearly, at least on the nutrition end, animal data, it might be a little tricky. On the training end, animal data might actually be more applicable. But again, the food and nutrition stuff, I mean, particularly all these studies with rats, you got to be a little careful with interpretation. But I think when you're dealing just with pure muscle physiology, I think the animal data is really interesting. Yeah. Again, very tightly controlled.
Yeah, exactly. And I think, especially when it comes to nutrition, people often criticize observational studies, and just like people that really don't have any knowledge about how the scientific processes work will say something like, oh, well, why won't you do a study instead of an observational study? Why won't you do an RCT, for example? And you can't really treat humans like animals in these really controlled settings for an extended long of that, especially if you're looking at, like, if the end result is a disease, for example, or a worst case death. You can't really do that, and that's why a lot of it is observational data, and that again has its limitations.
Right. It definitely has its pros and cons, and you know, for instance, if you look at some of the coffee data, it's all observational. People who drink X amount of cups of coffee, they live longer, they have less type 2 diabetes. Obviously, it's not interventional, it's clearly observational. You know, and are there limitations? Yeah, there's crazy limitations, but you're not going to do, imagine this, you're going to get 500 people to volunteer for a long-term coffee drinking study, and they will be randomized into coffee drinking and non-coffee drinking. The people who are randomized into non-coffee drinking are going to kill you. They're going to be like, no, I want to drink my coffee. You know, so clear limitations to it. And I think this is where a lot of the weird arguments come in, particularly when you look at observational studies on red meat. Well, red meat does this. Well, no, red meat is safe. And the observational studies on red meat, unless you're a statistician, sometimes are hard to interpret because remember, they're not dealing with biological categories, they're dealing with statistical categories. And that's where people get confused. They're like, well, if you eat 4 servings of red meat a week, your risk of colon cancer goes up. Well, those aren't biological categories. All they've done is they put you into these little statistical parcels. So
yeah.
Again, but sometimes that's all you have. That's all you have.
Yeah, exactly. And one thing that I would like to mention is, especially when you read things like eating 1 hot dog a week increases your risk of cancer by 25%. So if you eat 4 hot dogs, like the percentage is 100%. People actually think that sometimes, that it's, if you eat more, the percentages go up. But one thing that I wanted to follow up on is, could you please just explain a bit more about the peer review process?
Okay, peer review, it basically goes like this. So let's say I submit a paper, or someone else submits a paper to journal XYZ, whether it's New England Journal of Medicine, JISSN, Journal of Applied Physiology. Typically, here's what happens. It either goes to the editor-in-chief or an associate editor. Let's take JISSN, Journal of the International Society of Sports Nutrition. I'm one of the editors-in-chief of the journal. When a paper comes in, it either goes to me or one of the associate editors, of which there are roughly, 7 or 8. Now, those associate editors or myself can actually outright reject or outright accept the paper if they choose. It's rare, but it happens. Typically what they do is they will send the paper, they'll invite maybe 2 or 3 other scientists to review it, and that's where the peer review comes in. It's your peers, it's your scientific peers. So they review it, they come back with a review that says they accept it with revisions, or they reject it, or something in between. I mean, it depends what the comments are. The associate editor or the editor-in-chief makes a decision based on the comments of the reviewer, either to tell the author to revise it and resubmit it, or to reject it. Now, clearly there are problems with that, because if you're reviewing a paper from a lab that competes with you, there's a clear conflict of interest, right? If both of you are doing research on, let's say, whey protein, and you got a paper that contradicts a paper you just published, you might be like, you know what? I think I'll beat the crap out of this paper just because I don't like it. I mean, I don't think people do that, but maybe subconsciously they do that. Yeah. And we try to avoid that, but, we're humans. We're human. It happens, things like that. But I think for the most part, peer review tends to be as fair as it can be. It's not perfect. And it's one of those things where scientists actually volunteer their time, and that's what people forget. They're not getting paid to review these papers. It's purely voluntary. And like, for instance, myself, I probably review anywhere from 12 to 24 papers a year, and it's hard as heck. It's hard as heck, and the amount of time to review a paper actually can be quite a lot. So that's the process, and I've sort of shortened the time frame because sometimes it takes up to a year to get a paper published, sometimes just a few days. It really depends on the journal. Now, I will say with JISSN, a lot of editors-in-chief will want to see every paper that comes through. I don't. I'm like, in fact, I tell the associate editors, if you want to accept it on your own, do it. Don't tell me. If you want to reject it on your own, do it. Don't tell me. You guys are smart enough to figure out if a paper's really bad or really good. Because if I have to look at every paper that comes through, it's like I won't have time to do anything else. I won't even have time to go to the beach. And I need to go to the beach. Yeah. So, I give a lot more latitude to the reviewers and the associate editors, whereas others are much more like, they're more micromanaging, which I hate. I hate micromanaging. And, they got to have their hands into everything. And I don't know how people have time for that, to be honest. So with JISSN, if you submitted a paper, Juma, I couldn't even tell you half the time who it goes to. I don't know who the associate editor is, who has it, and I don't even know who the reviewers are of the paper. I mean, I could probably, if I tried hard enough, I could probably find it, but it's one of those things where, you know what, we'll let the associate editor handle it, and let the process sort of take care of itself. Okay.
And why do people have issues with reviewer number 3?
With reviewer number 3?
Yeah.
Well, it could be reviewer number 1, too.
Yeah.
Here's what I typically do. If 2 people review a paper and one rejects and one accepts, I usually send it to a third reviewer. Yeah. If 2 people reject it, then it's done. If 2 people accept it, then it's accepted. But it's, who the most not critical, the most God, not difficult. They're the ones who tend to be the most, I guess the word's critical of a paper. And I'm going to give you some choices. The professor who's been doing research for 30 years, the grad student, the master's degree student, or the newly minted PhD. Who do you think is going to be the toughest? So grad student, master's degree, newly minted PhD, professor for 30 years.
The PhD, I think.
Believe it or not, grad students oftentimes are the worst.
Oh, really?
And the newly minted PhD, because they got to prove something.
Yeah.
Here's what's interesting. Guys and girls have been doing research for like 20 or 30 years. They're like, you know what? Okay, there are limitations. We know it. This part could be better. But overall, it does add something new to the literature. Yeah. So we could beat the crap out of it, or we could tell them, hey, improve it this way, and you get published. So it's I remember having a conversation with a friend of mine, and I can't mention the name because people know what paper it was, but he said, man, he emailed me. He says, do you happen to know who reviewed my paper? I'm like, no, but I guess I could look it up. And he said, please tell me it wasn't a grad student or someone who just got a PhD.
Yeah.
So I said, well, it's a couple of guys who just got their PhDs. Yeah. and I saw the review. It was like literally they had something to say about every line. I'm like, wow. Yeah. They're criticizing like where you put your semicolon and stuff.
Yeah.
You know, I don't worry about that kind of stuff. To me, I try not to ever rewrite a paper because if the English is bad, I just reject it and say, hey, get someone to edit it and resubmit it. But I don't rewrite papers. I just give sort of comments about, well, explain this a little bit more, or maybe you could do this to make it better. And usually it's questions of just in the discussion, explain the data a little bit more. And that's it. I mean, other things, and actually you might be interested in this. You might notice a trend in the sports sciences where people are starting to publish individual data points. Yeah. Whereas before, all you would get are averages. You know, Group A average with standard deviation bar, Group B average with a standard deviation bar. Now people are saying, show me the individual data because I want to see what individuals have done. Yeah. And to me, that is a big improvement because now you could see, wow, here's an outlier. He's way up here. Here's someone who did really bad. And then you have this cluster of people in the middle where you get sort of the average response. And to me, that alone tells you much more information than just looking at averages and standard deviations. And I sometimes will ask for that. I'm like, hey, how about showing me individual data points? Because I think it tells a better story than averages and standard deviations.
Yeah, exactly. I think it's a study by Ron Mon from, I think it's from 2003, where they looked at fluid intake and sweat loss for a Premier League soccer team. And they have the individual data points there. And the funny thing is, when you look at it, the guys that were sweating the most were drinking the least, and the guys that were drinking the most, the guys that were drinking the most were sweating the least. So it was really opposite of what you should have done. So
and you know what, you'd never see that if all you saw were the averages.
Yeah, so, exactly.
Yeah, so that's cool. I mean, that's really cool data.
Yeah. And sometimes if you work with athletes and you see some people criticize, there were some outliers there, but sometimes these outliers might be the athletes that you're actually working with, and that might be pliable for them because they usually are the ones that stand out from the crowd.
Yeah, and I always say you can learn a lot from the outliers.
Yeah, exactly.
Because there's something weird going on there. Yeah.
Oh. So after you've done the peer review process and it gets published, it finds its way to social media. It finds its way on Facebook. And then
that's peer review number 2.
Peer review number 2, and then the real criticism starts. So what, like for people that comment a lot on Facebook and criticize studies, like what would be the take-home message that you would want to tell them of the thought process they should go through before starting to criticize a paper?
Well, I think what I would suggest they do is first look at every study sort of as a big picture thing. What important or significant piece of information can I get from this particular study? And when you look at it sort of from the big picture, you tend to pick less on the minutia. Instead of nitpicking little details, you're like, oh, okay. Like for instance, there was that recent study, I think it was Tipton's lab, showing that 40 grams of protein did better than 20 grams of protein in terms of acute muscle protein synthesis.
Yeah.
Which is different than the original study showing that you seem to plateau at 20 and 40 didn't help much more.
And they were doing full body
right
split as well.
Right. And here's the thing. It's like, okay, the exercise stimulus was different. So that should be something to keep in mind. And also, to me, rather than focusing so much on the nuances and minutiae of the study, think about what would be, if I were a scientist, what would be the next thing to do? And I would say, well, if 40 grams of protein helps more when you're doing whole body exercise, how much would it help if you're doing not only whole body exercise, but really just very difficult exercise? Because when you think about it, usually the kinds of exercise that are in studies are not quite as hard as what you see competitive athletes do.
Yeah.
I mean, have them do something really hard and maybe it's 50 grams. I mean, who knows?
Yeah.
But people tend, I remember when the 20-gram study came out, people were like, well, see, all that extra protein you're drinking is just a waste of time or a waste of money. And it's like, well, no, it's not a waste. And two, it's just one study. And three, the exercise stimulus was really quite limited. So you have to sort of, think beyond just the minutia of the details of the study and think big picture. Now, I would say every study is easy to criticize. It is. In fact, that's one of the first things you learn in graduate school. It's like, you know what? There's no perfect study. Yeah. If you want to beat them all up, you can beat them all up. It's easy to do. It's very easy to do. And so I think for those who have never done research, they should sort of sit back and think, what could I learn from the study versus how could I show everyone I'm so smart that I can point out the limitations of the study? And you know what? That's easy to do. Anyone can point out limitations of a study.
Yeah, exactly. When it comes to the final question of the day is, let's talk a bit about the hierarchy of evidence, because I know that you see these pyramids where you'll find meta-analysis and systematic reviews on top, and then it goes down from there. And I know you have some opinions about that. Could you please share it with us?
Yeah, you'll see this hierarchy of evidence that people at the top, though, in terms of the importance of information in science, that typically at the top you'll see reviews or meta-analyses, and under that you'll see randomized controlled trials or RCTs, and then below that you'll see other things like observational studies, case studies, animal studies, whatever. Yeah. And to me, you almost have to separate reviews and meta-analyses and pull it out of the pyramid, and here's why. Reviews and meta-analyses are basically just snapshots of the current evidence available. It's sort of like you got a camera, you got a subject, you take a picture, and that's all you got. You got a picture. But without a subject, there is no picture. Without RCTs, particularly in our field, there is no science. If you remove every RCT from the sports science category, not only is there no science, there's no reviews, and there's no meta-analyses. So the thing that makes science rock and roll are the randomized controlled investigations or original investigations. Without the RCTs, reviews and meta-analyses are just a waste of time. And in fact, if you want to make an original contribution to the field, it has to be in the form of an RCT, because that's what moves a field forward. And it's just so funny. You always see that hierarchy, and it's like, and as a scientist, I look at it and I'm like, this is total baloney. Who thinks this? But apparently a lot of people think it. They're like, well, reviews are at the top and meta-analyses or whatever. I'm like, that's baloney. That is absolute baloney. If you want to change a field, it has to be through an RCT. And let me give you some concrete examples. Way back in the 70s, a guy named David Kostel did some research comparing caffeinated and decaffeinated coffee. It was one of the first studies that showed the idea that if you consume caffeine, it helps exercise performance. An RCT, not a review. In the 1990s, a guy named Shalander Basine published a study showing that if you administer testosterone and anthate to healthy males, not only did they get bigger with exercise, but they got bigger without exercise. Yeah. And secondarily, there were no side effects. So it was an RCT that changed the view of anabolic steroids, not a review.
Yeah.
So those are two very, very sort of poignant examples where someone had to do the RCT to change the category. You see, and also creatine. Roger Harris did some of the original work on creatine. That changed the category because he did an RCT. No matter how many reviews and meta-analyses are done, those will never change the way science moves forward. Again, it's a snapshot.
Yeah.
You don't want a snapshot, you want a movie. And if in order to get a movie, you got to do the RCT.
Yeah.
That's what changes a field, and that's ultimately what we need. We need RCTs.
Yeah, exactly. And I'm currently doing the IOC diploma in sports nutrition, and what they teach us there is try to read as much original data as possible. And the way that they actually teach us to use the meta-analysis and the review is when you want to actually investigate a new topic, read the reviews and the meta-analysis first, so you will get an overview of the literature, and then start to read the original data.
Yep, and you know what's funny? That's exactly what I tell students.
Yeah.
Start with the broad base, and then you might find something within that broad base that interests you, and narrow it down, and then start looking at the original investigations. Because that is the nice thing about reviews and meta-analyses. It gives you that snapshot, which sometimes that's what you got to do. And for instance, I'm starting a new research avenue looking at the microbiome and the effects of diet and supplementation on gut bacteria and whatnot. And I know nothing about the gut microbiome. Yeah. When I first started this, I'm like, I guess I better find a good review, because I didn't even know where to start. So I picked up some reviews. I'm like, oh, okay. And then I started reading some of the interesting stuff on probiotic supplementation and body composition in animals and obese humans. I'm like, oh, there's some cool stuff here. Then I started pulling out some RCTs. So, but I had to start somewhere, and reviews and meta-analyses are a good way to start to see a nice snapshot of the category.
Exactly.
Yeah.
All right, Joey, always a pleasure to talk with you. Thank you so much for doing this podcast.
Hey, thank you. And hopefully the temperature will rise like 10 degrees centigrade where you are.
Yeah, hopefully. Like I said before we started, we've had a really turbulent summer here in Norway with temperatures some days really hot, and then the next day it's rain and dropped like 15 degrees. And as soon as we hit August, 1st of August, it just dropped like 10 degrees right away. So yesterday when I drove my dad to the airport, it was like 6 degrees, and we're still in we're still in August. So yeah, it's going to be a tough winter. So yeah. Okay, before we sign off, where can people find more information about you?
Probably the easiest way to get to me would be through Facebook. I usually just post paddling pictures, but I occasionally will post science stuff on the ISSN discussion group, and also through the ISSN website. It's the address is issn.net, issn.net. And also, just as a reminder for the people who listen to your podcast, our national conference is every June, and next year it'll be June 22 to 24 in Phoenix, Arizona. It's a good reason to go visit Arizona. You could visit the Grand Canyon. And by the way, it's a gigantic canyon, hence the name Grand. So come to the science conference, and when you're done, go say hi to the Grand Canyon next year.
Excellent. All right, Joey, thank you so much. For everyone that's listening, this podcast will be available on in video format on YouTube, but you can also listen to it on iTunes if you want. Sounds good, Joey? Thank you so much. Yeah, and we'll talk soon. Bye-bye.
Bye.